folks, I hope you're enjoying the first day of your 3-week school vacation brought to you by COVID-19. Remember that the purpose of being away from school is so that we can be away from each other and help deter the spread of the virus. Use this time to sit at home and relax. Keep washing your hands, stop touching your face, and try your best to not interact with too many others. Today we're going to tackle part 2 of our organic chemistry notes. In this lesson you'll be learning about some more functional groups and the structure and naming of acyclic alkenes and alkynes. So let's get started. We've already learned what to do with functional groups made of hydrocarbons, otherwise known as alkyl groups. We name them like the alkanes they are, but put the YL ending at the end. So one carbon is methyl, 2 carbons is ethyl, and so on. Another really common group to see attached to a hydrocarbon is a halogen, or an alkyl halide group. If there's a fluorine attached to our hydrocarbon, we call it a fluoro group. Chlorine is chloro, and so on. When naming our hydrocarbons, we use these just like we do the alkyl groups in the naming process. So let's do some examples. First, locate the parent chain and substituent groups. Number the parent chain starting with the carbon closest to a substituent group. Then write out the name. Remember to list your substituents in alphabetical order. What do you get for the first example? I got 4-bromo 3-chloroheptane. For our second example, it's a little trickier. We would hit the first substituent group on the third carbon no matter which way we number from. In this case, you want to go with whichever substituent group comes first alphabetically. Bromo is alphabetically before methyl, so let's number from the right side this time. What do you get for the name? I got 3-bromo 4-methylhexane. See, that's not so bad, is it? All right, let's talk about alkenes. Alkenes are hydrocarbons with at least one double bond. Alkenes with just one double bond have the general formula of CnH2n. In other words, if there's just one double bond, there will be twice as many hydrogens as there are carbons in our hydrocarbon. To name alkenes, number the longest carbon chain starting with the carbon that's closest to the double bond. Name the substituent groups as you would in alkanes. The only difference is that sometimes we have to indicate how those groups are arranged around a double bond. We'll talk more about that in a second. The root of your name is similar to alkanes, except we have the -ene ending this time. We also have to place a number in front of our root name to indicate which carbon that double bond starts on. You'll see this when we build physical models of these, but a double bond restricts the carbon's ability to rotate around. Since that rotation is restricted, the substituents attached to both of the carbons in a double bond are stuck where they're at. This creates geometric isomers, and it's the reason we have to specify how our groups are arranged around a double bond. In order to have geometric isomers, each carbon that's a part of the double bond has to have 2 different groups or atoms attached to it. If either carbon has the same 2 groups attached to it, for example, 2 hydrogens or 2 methyl groups on the same carbon, it cannot have geometric isomers. We name these based on where the similar groups or atoms are. If they're on the same side, we call it cis. If they're on the opposite side, we call it trans. This indicator goes right before the number that indicates what carbon the double bond is attached to, right before the root name. So let's do some examples. The first one is relatively easy. Start your numbers on the right side. You get that there are 8 carbons. Specify which carbon your double bond starts on, carbon number 1, then put the rest of the name. Since our first carbon is attached to 2 hydrogens, it can't create geometric isomers, so we don't have to indicate cis or trans. What do you get? I got 1-octene. For our second one, do the same thing. Remember to start from the carbon closest to a double bond. Name the groups like you would an alkane, and since each of the 2 carbons on the double bond are bonded to 2 different groups or atoms, we have to indicate whether they're oriented in a cis or trans way. What do you get? I got 3,4-dichloro cis-3-heptene. Try the last one on your own. What do you get? I got 3,4-dibromotrans-3-heptene. If our alkene has more than one double bond, we name it basically the same way, but there's an extra little step at the end. You have to include a prefix, di, tri, tetra, etc., before the "ene" part of your ending to your root name. This is often preceded with an extra "a" to give the name a nicer flow. For example, 2 double bonds would be a diene, 3 double bonds would be a triene, and so on. So let's do some examples. Go through all the steps to name the first example here. You'll have 2 numbers right before your root name because there are 2 double bonds. Don't forget the cis and trans. That goes right before each of those 2 numbers, indicating where the double bonds are. What do you get? I got trans 2, trans 4, heptadiene. How about the second one? In this case, no matter which way you number your chain, you get a double bond on carbons 2 and 4. If that's the case, you have to go with whichever gives you the lowest substituent numbers. Either way, you have one halide group on the carbons 2, 3, 4, and 5. So go with whichever side has a substituent group that is alphabetically first. That'd be bromo. So number from the right side this time. What do you get? I got 2 bromo, 3, 4, 5 trichloro, trans 2, cis 4, hexadiene. Whew, that is a big name. Now I'm not sure you've learned enough yet, so let's talk about alkynes. You can have all kinds of fun naming these molecules. Alkynes contain a triple bond and, assuming there's only one triple bond, they have the general formula CnH2n-2. That means there'll be twice as many hydrogens minus 2 for however many carbons you have. These follow the same rules as alkenes when you name them, but we end our name with the YNE or the "ine" ending. Since the carbons on either side of a triple bond can only be bonded to one other group or atom, there are no cis or trans geometric isomers. This also makes our line structures look a little funnier than usual because the lines go straight out on either side of a triple bond. Let's do some examples. Follow the same general rules as usual. What do you get for the first one? I got 2-butyne. How about the second one? Either way you number the chain, the triple bond lands on carbon number 4. So number with the first substituent or first alphabetically if they're the same. What do you get? I got 3-fluoro-6-methyl-4-octyne. We didn't do an example of it, but if you had multiple triple bonds, you would treat that the same way you do when you have multiple double bonds. So you could have a diene or a triene or whatever other prefixes you need to indicate how many triple bonds you had. All right, the moment you've all been waiting for, the last slide. Alkenes and alkynes react in 2 very important ways: addition and polymerization reactions. In addition reactions, we add extra atoms or groups to an alkene or alkyne. This forms new single bonds using the electrons from a double or triple bond. What that usually looks like is an alkene turning to an alkane with some extra groups on the 2 carbons attached to the double bond. Or an alkyne turning into an alkene with some extra groups attached to the carbons on the other side of the triple bond. Polymerization reactions involve small molecules using their double bonds to bond with other small molecules, forming a much larger molecule called a polymer. Polymers are what plastics and rubber are made out of. The repeating units within a polymer are called monomers. If we fully wrote an equation out, it might look like this. Notice the double bonds disappear and form single bonds between each of the monomers we added together. The general form of that reaction is N, then our molecule with a double bond, gives us in brackets the monomer with a subscript N at the end. That says that based on the number of original monomers we threw together, they linked up and created a chain of repeating monomers that's the same number long. We'll do more with both of these reactions later, but for now, keep those on your brain. Well, that's it for today, folks. If you have any questions, please let me know.